Hello friends, today we will learn radical functions, radical forms, radical functions, square root functions, and cube root functions. So before starting, we will try to see what these actually mean: x to the half, x to the one thirds, and those are rational exponents. What you see here, these are called rational exponents, and what you see here are radicals. So a rational exponent is something that has a fraction as the exponent, and a radical function is where you have the square root form, just like this. So we'll try to see how to convert between these two as we go. So if you see the first question here, how is x to the half written as? The denominator here is 2 in the exponent, so that will go into the cup as a square root. And the 1 is the numerator which stays with the x as the exponent. And that's how it is written. Normally, for a square root, by default, we understand it as a square root function. We don't have to write the 2 if it is 2. So that's why it is a square root function. So we'll say square root. So by default, if no number is there, it is square root. It is assumed that it is square root. But when it comes to x to the one third, and from now on, any number other than 2, we must write it in the cup. It's cube root of x. Because it's a 3, we say it's cube root of x. And here we have a 2 again, so we don't have to write the number. But this 3 will go as the numerator, or it will be the exponent, x cubed. So square root of x cubed is what it really means. So as a practice, you can think of how this goes. Like, let's say x to the power of 1/5, right? You can pause the video to write what it is, okay? So x to the 1/5 is fifth root of x, okay? We say it fifth root of x. X to the 1 over n means nth root of x. So n goes into the cup and we say it as nth root of x. All right, this is how it goes. And if you have m over n, the n in the denominator goes into the cup, and the m in the numerator remains there as the exponent inside the root. That's how we write it. So this is the most important thing. So if we have to convert back a radical into a rational exponent, you have to remember this is 2 by default. So that goes into the denominator of the rational exponent. Okay, so if you see 4 halves reduces to x squared, right? That's how when we square root something, the exponent becomes half. Okay, so here likewise you have x here, the 7 goes into the numerator and the 3 goes into the denominator. All right, x to the 1/5. You can pause here and write answers for the others, but I'm just going on. Okay, so that's how you get the answers. I hope you understand this. So this will be a helpful concept for us to solve if they're rational exponents, right? So if they're rational exponents, so here I'll write this big, x to the 3/4 equals 7. We need to bring this as x equals, meaning the exponent should be 1. How would I make this 1? Only if I multiply the exponent with the 4/3 so that these will cancel off. But what we do on the left must be done on the right side also. So we make 4/3. So if we flip the original exponent and multiply it, we get 1 here and we get 4/3 here. So we don't have to do all of this work every time. When a question is given x to the 3/4 equals 7, all you have to do is flip the exponent and put it on the other exponent. Okay, so it's like x equals 7 to the 4/3. and you're good to go. And this comes to be some 13.95, something like that. You can use a calculator. Okay. Okay, so let's practice. So here we have x to the half equals 5, meaning we are flipping the exponent here to 2 over 1, which is 5 squared. And 5 squared is 25, right? Okay, so that's how you can pause to get the other two. So this x is 729 to the power of 2/3. Yes, you can use a calculator, but what if such question appears in the SAT and in a non-cal section of the SAT? So if you see, the hint is the denominator here in the exponent. If there is a 3 here, this 3 must be cancelled. If that 3 must be cancelled, then the base must be a cube of something, right? So it happens so that 729 is a cube of 9. So 9 cubed to the power of 2/3, and hence the 3 will cancel. So we have x equal to n squared, which is 81. That's how you get this. Okay. If you do not understand, just rewind and then play again. So I'm going ahead to solve the next one. You can pause the video to try it by yourself. So x equals 64 to the power of 4/3. So that's what I did. Just flip the exponent and put it on the other head. But 64, if you see, we need a 3 here to get cancelled. That means 64 is a cube of something. So 64 is a 4 cubed to the power 4/3. So 3 will cancel. We are left with 4 to the 4. This is actually 256, but to simplify, you can write it as 16 times 16, right? Which is also 256. Okay. There are some certain numbers that you must remember the squares of. I would recommend you to remember the squares of numbers from 1 through 20 at least. And it's good to memorize them and have them committed to memory. Likewise, if you have cubes, I would strongly recommend you to remember at least until 1 through 10 of 10 cubes. Okay. All right, now let's move on to the next topic here. We'll actually learn how a radical function looks like. Now we are particularly looking at square root function here. So if we choose certain numbers, right, and when you plug in square root of -1 in the calculator, it will throw an error because square root of -1 is imaginary. So that cannot be drawn on a Cartesian plane like this. So the next choice is 0. So what we would write here, we would say this is not applicable. Okay. Square root of 0 is a 0. Square root of 1 is 1. We'll take 4 here instead of 2. Square root of 4 is 2. So when we plot these points on the graph, this is what we get. Okay. So this is a square root function. If you see, it is the end point is 0, 0. That's what they say, end point, start point, or terminal point. But the bottom line is the domain is only x values beginning. Sorry, what did I do? My bad. Okay, so we'll start over. It's going to go like this. So the domain is all x values starting from 0 through infinity, right? Same way, if you see, the range is starting from 0 through infinity, the y values. So the domain here is, in set notation, x belongs to all real numbers such that x is greater than or equal to 0. Range in set notation is this time y belongs to all real numbers such that y is greater than or equal to 0. In interval notation, you're experts in this field. Okay. Now both are intercepting the x and y axis at the origin. Okay. This graph has a minimum value at 0. Right. So all of this is about square root function, the parent function of square root functions. So if we have to move the graph, then we'll have to go over all the transformations. Like if A is greater than, if A is negative, A is negative, then then we have vertical reflection. All of this, I'm going to upload this particular transformations in a separate file. I don't want to talk about it all over in this video. It would be too long, but you get the idea. This is same as what we have done so far in every function. All the transformations. A gives the stretch factor, the vertical stretch factor. B gives the horizontal stretch factor. X minus h is the naughty child, and where it moves right when it is x minus h, x plus h will make it move left. And k is the good child, which goes up and down according to plus and minus. So same kind of thing here for a cube root function, except for that this time a cube of a negative number is a valid real number, which is also negative 2, which means that these values are possible, right? So this will be negative 2, negative 1, 0, 1, and 2, right? And when you draw the graph, this is how it will look like, which means the domain here is all real numbers, and so is the range. So, so the interval notation would be negative infinity, infinity, and so will be the range. And both are intercepting the x and y axes at 0, 0, the origin. All right. So the min and max value is not applicable here. It's all infinity. So the same kind of transformation function is as same as above. I'm going to upload the image of all the transformations in a separate file. Please check that out. So this is what we did on the first day of this unit, and I'll come back to you with the second day's video shortly. Thank you so much for watching.